I will begin. So I think the first thing I should do is talk, the thing I haven't hit on yet in in section 6.1 is the graph of like the rational functions, right? So that's one of the things we want to learn at least a little bit about, because visualizing the root functions can be helpful for understanding how they behave, you know, especially like for estimation, things like that. So, although you're like, I've got a calculator, so I don't care. It's hard for me to argue that, but nevertheless, let's talk about graphs. Of y equals the square root of x and y equals the cube root of x. So I'll call it example 1, square root of x. All right, so like the domain, what's the domain of the square root of x? It starts at 0. And it goes on, right? So what's the square root of 0? The square root of 0 is 0. Square root of 1, right, is 1. And let's see here, 2, 3. By the time I get over to the 4, square root of 4 is what? It's 2, right? So if I get over here, 1, 2, 3, 4, I go twice as far up, right? So it's growing relatively slowly as we're, you know, used to things. And so then the graph looks something like that, right? So this is the, and if I did it right, it's coming in here real steep like. Okay, like that. This is y equals the square root of x. And if you know that, then you can create some other graphs if you wanted. Like, what would the square root of x minus 1 look like? Actually, before I do that, well, okay, yeah, an example in your book has a square root of x plus 2. So let's do, so this would be square root of x, right? So you can kind of see things from here, right? Like, what was the square root of 2? Square root of 2 is what? It's like right here, right? That would be 2 comma square root of 2, that point. And you can see that that's some number between 1 and 2, right? So anyway, what would the y equals the square root of, let's say, x minus 2 look like? So the way this is, you move y equals square root of x 2 units right. So the graph of this guy, so let's see here. What's the domain of this one? So what you need is you need x minus 2 to be greater than or equal to 0, right? The radicand has to be non-negative. And so that gives us x is greater than or equal to 2, right? So that's 2 to infinity, right? So the graph of the square root of x minus 2, it doesn't start at 0. This one starts at 2. Starts here at that point 2 comma 0. and it looks like this, right? So like over here at 3, this point would be like 3 comma 1. Because if you plug 3 into the formula, you get the square root of 3 minus 2, which is the square root of 1, which is 1. And then if you keep going out here, 3, 4, 5, eventually you get over to 6, where the function's got it all the way up here to 2. But, yeah. This is the same shape, just shifted over, right? If instead of having minus 2 or here, you had plus 2, it would take the graph and it would move it this way 2 units, right? So
minus to the right.
Exactly, right. That's also true for like other kinds of graphs, like if we have y equals x squared. Well, it's just a quick reminder. If you have y equals x squared, what's that look like? Looks like this, right? Y equals x squared. So if we have, here's y equals x minus 1 squared. Here's y equals x plus 1 squared. So as you can see, taking the formula and replacing x with x minus 1 will move it 1 to the right. If you replace x with x plus 1, it moves it 1 to the left. That's the way graphs work when you modify their inputs. Now, in contrast, right, what would happen if instead of modifying the x part, you just added or subtracted 1? Well, that's a different story, right? On the other hand, we have this one or this one. This is y equals x squared plus 1. This is y equals x squared minus 1. So it's really different the way the graph modifies if we shift different parts of the formula. Like if we just shift the whole formula by either adding or subtracting, we just literally shift up or down the graph. But if we replace the x in the formula with x minus a number, it shifts that number to the right. If we shift it by x plus 1, plus that number, it shifts that number to the left. Now, I think these things are useful to know. I'm not sure if they're tested directly in your homework, okay? But, yeah. Right. Maybe that's actually in chapter 7, actually. You never got 7? Huh. Maybe that was in... Huh. I mean, there are examples like this in section 6.1, like numbers 30 through 40 are like that. But they're more complicated than just that. There's also like... well, let's work some of those, actually. That'd probably be helpful. So I don't think this is in your homework, but I think things like that are in your homework. Now, whenever you're facing a graphing problem, one of the things you can do, of course, is just plug in points, right, and connect the dots, so to speak, right? So example 4, you might have something like, here, I'll work a somewhat hard one. Y equals the square root of 12 minus 3x. So we could try to understand that in terms of transformations of graphs, but I think it's just better at this stage in the game to use like just plugging in values and working it out step by step, yeah? So the first order of business, though, is like, where are we looking at? Like, what's the domain of this? That's the main thing, right? So we need 12 minus 3x to be non-negative. We need to be greater than or equal to 0. That's what the radicand has to be. And so that gives us 12 is greater than or equal to 3x. Then dividing by the positive number 3, I get 4 is greater than or equal to x, aka x is less than or equal to 4. So that tells me that the domain of the square root of 12 minus 3x is actually minus infinity to 4 included. So to understand what this graph looks like, I probably should make a table of values that has 4 as its rightmost point, and then go more negative past that, right? Like, so I'll make my table of values here. Here's my x, here's my square root of 12 minus 3x. So this is going to give me, and then over here I'll put point on graph, which is kind of a duh column, but there we go. Anyway, so let's start with 4. That's an easy one. So we get the square root of 12 minus 12. 3 times 4 is 12, right? So we get 0. So the point on the graph, 4 comma 0. All right, now we want to pick another point, which is, to the left of 4. What do you want to do?
I just pick one.
I mean, we do 3. I'll do 3. So we get square root of what? 12 minus 3 times 3, which is 12 minus 9. Yeah, square root of 3, right? So that gives me the point 3, comma. And square root of 3 is approximately 1.7 something. I forget. But I'll just say 1.7. Okay. And then 2. All right. Square root of 6. And square root of 6 is what is the square root of 6? Well, so the way I think of it is like this. So here's how I think about approximations, right? The square root of 6.4 is, oh man, it's not right. Oh, never mind me. So what you got? Square root of 6 is what? The decimal? What is it? Is about? Oh, it's the calculator's too smart for its own good, huh?
No, yeah, I did it like. This is 1.56.
1.56. Maybe that's right, 1.56. Let me just, I'm sorry. For some reason that seems wrong to me. So if I square 1.56, right? That's basically the same as 1.5 squared, which gives me 2.25, I believe. So no, I don't think it's 1.56. It should be bigger than 2 and less than 3. 2.44. Okay, so this is 2. You pressed the wrong button? Yeah, these things will happen. 2.44. So 2.4. We're just going approximate point on graph, all right? So let's see here. How about 2, 3, 4? What's next here? We got what? How about minus 4? Well, that's too far. What am I going to? Let's go 1. That's square root of 9, right? Zero. Square root of 12, right? So what we got here? 1 comma. Oh, I knew. Hey, I can do that one. 3. And what? 0 comma 3 point. I don't know. We're offhand. Think about it. 3.4. 3.5.
Square root of 12?
Yeah.
3.4.
3.4, okay. Okay, so I think we've got enough. So our graph starts at 4. So we start at 0, right? Then when we get to 3, we're at 1.7. So let me see here. We draw myself some guidelines here. Roughly speaking, as well as I can do anyway. That's 3, 2, 1. All right. So at 3, it was 1.7. So it's like here-ish. And then at 2, it's 2.4. And at 1, it's 3. Oh well, I tried. At 0, it's 3.4. Anyway, so it's something like, roughly speaking, something like this, right?
So you didn't have to do the 1 and 0.
Yeah, I mean, if you get a few points in here. Now, if we were smarter, we would have, here's the other way you could do this one. If you want to do it by, like, instead of table values, like, do it by algebraic thinking. So this is the square root of 12 minus 3x, right? Which is the square root of 3 times 4 minus x, which is the square root of 3 times the square root of minus x minus 4. So I don't know if it's really good or not, but you start with the square root of x, right? Then you shift that shift it 4 to the right, like here, right? So step 1, and then step 2 is if you replace this with minus that, what that does is it flips it over here like that. And then final move, multiply it by the square root of 3. That just makes it dummy. Me, not you. How about this step right here? Bunch of nonsense. Multiply that out. Did you get back to here? No. That's supposed to be a plus. Plus, which means I should have done which means I would have first shifted 4 to the left, like this. All right. And then when I'm going to write it right here. Then when I put that in, this would be y equals square root of minus x plus 4. It just flips the graph over like that. And then, final blow, you take it and multiply by square root of 3 to make it taller. So I don't know. I think this way of thinking for this problem is definitely the wrong way, right? And also, I don't think these things are clearly spelled out in your book, so this is not how you're expected to think anyway. Maybe you had a high school algebra class where you learned transformation of graphs in terms of like a stepwise series of transformations. What's that?
We didn't learn all this.
Oh, okay. Yeah. There's basically you can horizontally shift by adjusting the x input. You can vertically shift by adjusting the y output. you can, and then you can like, if that's all by positive stuff, like if you just multiply your function by -1, it flips it over the y-axis. If you replace x with minus x, it like flips it that other way. And then there's also multiplying, which will like stretch things out or compress them depending on what you multiply. Anyway, table of values is the way to go here. So let's stick with that. Let's do another one right quick. So this, by the way, was example, I got this from your book. This was number 39 from section 6.1. So example 5. This is number 34 from section 6.1. We're dealing with f of x equals 2 plus the square root of x minus 1. So we can either use, this one, the transformation of graphs idea is pretty easy. We start with y equals square root of x. All right. Then we, square root of x minus 1 takes this one and shifts it 1 like that. Then, so shift right 1, and then we shift up 2. So the graph is going to basically look like that. So this point was 1, 0. This point now is 1, 2.
I made that sound, I thought it was a lot harder, but it's really not.
Yeah. Yep. Now, as I was saying, table of values is a more safe method for you guys. The table of values, to be done logically, we need to first address what's the domain of f of x, right? It needs x such that x minus 1 is greater than or equal to 0. Like that's what we need. We need the radicand to be non-negative. So that's just what? X greater than or equal to 1, right? So the domain here is 1 to infinity. So if we take the table of values root, here's my x, here's my y equals square root of, oh, goodness gracious, forgot my formula. Y equals 2 plus the square root of x minus 1, right? So I could do like 1. So I get y equals to 2 plus 0, right? So the point on the graph is what from these? It's 1, 2, right? And then if I'm smart, I will not do 1, 2, 3, 4. I'll skip ahead to make my life easier. So I think about what would make that 4. X equals 5 would make that 4. I'm going to skip ahead to 5. That's easier. Y equals to 2 plus the square root of 5 minus 1 is 4, which is 2 plus 2, which is 4. So I get 5, 4 is another point. And if I'm going to keep on with this lazy root, I want to get to 9 because 9 is the next nice square number. So yeah, x equal to 10. And that gives me y is equal to 2 plus the square root of 9, yeah, which is giving me 10, 2 plus 3 is 5, yeah. So if I'm here at 1, 2, 3, 5 is here. So there's 10. Let's see here. 1, 2, 3, 4. If I had graph paper, this would be like neater, right? And so we start at the point 1, comma 2. Right? And then we go to the point 5, comma 4, over 5, up 4. So the best of my artistry about there. And then we go to 10, comma 5. So, and then it keeps going. So there you go. There's a pretty decent graph of y equals to the 2 plus the square root of x minus 1. When you draw the graph carefully, you can answer questions easily, like what's the domain of the function? Well, the domain of the function is 1 to infinity. Those are the x values you see on the graph. What's the range? We could also answer that question. What's the range of 2 plus the square root of x minus 1? So the range is the set of allowed y values for the function, right? The y values which are actually attained, I should say. What do you get there? So if you look at it, it's easy to see, right? It starts at 2, and it just keeps going and going and going. So the answer is 2 to infinity. All right. So that's all I got to say about graphs of square roots in here for you guys. Let me shift over to cube root. Okay, what's the graph of the cube root look like? So I think this is example 6, isn't it? So y equals the cube root of x, right? I'm going to go a really different way of thinking on this one, okay? So this, if I cube both sides, I get y cubed equals to the cube root of x cubed, yeah? Which is x. So in other words, this is a cubic where the roles of x and y are reversed. So to graph a cubic, I can think of this as y and this is x, right? So what would the regular, if we just had y and x and we draw y equals x cubed, it looks like this, right? So if I'm interchanging the roles, I just do like this. So it's the same shape, it's just turned on its side. That's the cubic. Now I can add some points here, like the cube root of 0 is 0. The cube root of 1, this point is like 1 comma 1, right? It's also got the point minus 1 comma minus 1, right? And if you get out far enough here, you get over to 8 comma 2, because the cube root of 8 equals to 2. And if you get far enough the other way, you got minus 8 comma minus 2, because the cube root of minus 8 is equal to minus 2. So this is what the cube root looks like. It's interesting, really different looking shape. And anyway, the domain of the cube root is what? All reals, right? So the domain of the cube root is all reals. What's the range of the cube root? Again, all reals, because it keeps going this way and keeps going that way. All right. Enough about all that. Let's move along here. Let us work some simplification of exponent problems, because we need more practice on that. That is certain, right? That is certain. So, before I erase this though, what if I had the cube root of x plus 1? What would it do? It would just take this picture, shift it up 1. Cube root of x plus 1 would be just up 1, right? If I had the cube root of x minus 1, it would take this whole picture and just shift it right, like that. And again, if in doubt, go back to a table of, what is it? I see confusion, so I will
You said if it was plus 1, it'd go up. If it's minus, it'd go to the right.
yeah, so if it was plus 1, so here's the difference. If it was bad, something like that, horribly written, right? So I'm just adding. So I mean for it to be the same shape as this, just shift it up 1. But this would be y equals cube root of x plus 1.
Okay, how you were saying it, but
Yeah.
both times in what way? That can't be right.
Yeah, I'm sorry. You know, English lets us down for these kind of discussions.
I thought you meant like.
Yeah.
minus.
Sorry.
That should be going down.
I probably said it wrong. We can review the tapes later, or not. Okay, so I do find that graphing rational functions is helpful as I'm thinking about solving problems. So maybe it's worth our moment of our time to look at that for just a second here. Suppose you were going to solve, 2 plus the square root of x minus 1, right, equal to, say x. So if I think about that, the picture we graphed this a second ago, right? And we figured out that it starts out at 2 and it kind of goes up like that, right? And what does y equals x look like? It looks like this, right? So it seems reasonable, it seems plausible to suppose that there's going to come a point, right? There's going to come a point where those two guys meet. And where those two guys meet, where that intersection point is where both of these equations have the same y and thus are equal. And so graphs allow us to anticipate algebra solutions if we think about them. And now how would we actually solve this, though? See, this is kind of a tough problem, a little bit. So what we're going to do is isolate the radical. And I just made this problem up, so the answer might be quite ugly, okay? The ones that are in the book tend to have answers which are whole numbers, right? But I just made this up, so all bets are off. What's about to happen could get ugly. So isolate the radical, and then to get rid of the radical, square both sides. Okay? Now that gives me x minus 1 equals x squared minus 4x plus 4. Which we can, hey, that's a quadratic equation. We know how to solve that. So we got x squared minus 5x plus 5 equal to 0, I think. And don't believe it factors, so I'll complete the square on this guy. X minus 5 halves squared minus 25 over 4. How many fourths is 5? 20, right? 20 fourths. So this gives me x minus 5 over 2 squared equal to minus 25 plus 20 is 5, so we get 5 over 4 over here. and then this gives me x minus 5 over 2 equals to plus or minus the square root of 5. That was supposed to be 5 over 2. So I get x equals to 5 halves plus or minus the square root of 5 over 2. So what is the square root of 5? $2.23, right? So we have x is equal to 5 plus square root of 5 over 2, or 5 minus the square root of 5 over 2, right? This is x is equal to 5 plus, so about 7.23, right? Or, well, let's see here. 5 minus 2 point, what? 2.77 over 2, right? So this is approximately what? 3.6-ish, or 1 point.
I think the big best is 2.76.
2.76. What's that divided by 2?
You want a fraction of this?
Decimal?
1.38.
Okay, so then the question is, wait a minute, we got 2 answers. Which one of these is right? Are they both right? See, I think if you look at this graph, even with the crudeness of our graphing, it should be somewhat clear that probably 3.6 is the real answer. Yeah? Yeah, I think this is the real answer. Where is this 1.38 coming from? It's coming from the fact that if you were to look at y equals 2 minus the square root of x minus 1, right? The graph of y minus the 2, see this one here, the y equals minus 2 minus the square root of x minus 1? That would have actually given us the lower half down here. See? And if I had that instead of this, and I would have isolated the radical, instead of having a plus here, I'd have had a minus, but when I square it, I get to the same quadratic equation, you see? So, like, geometrically what's happening is we're picking up on this intersection point of an equation that we're actually not given. But when you have 2 answers like this, what you have to do is you have to go back to the starting equation and plug them back in to make sure to figure out which one's quote-unquote extraneous. So this one is extraneous, I believe. Now, we can check it. So the question is 2 plus the square root of 1.38-ish minus 1, right? Is this equal to 1.38? That's what it would take for it to equal here, right? Well, look at that. That's obviously false. So we have 2 plus a positive thing is equal to 1.38. Nonsense, right? So indeed, this is extraneous. We have adjoined that to the answer by when we square things. Whenever you square an equation, you can be adding solutions. That's what happened. So the answer is just x equals 3.6. I would point out that graphing this side of the equation and knowing how to graph a line paired together guided my algebra. That's my larger point here. Another thing I tell students is that if I was to be a rapper, I would be extraneous G. And then I would tell them that I'm not even in the solution set. So, almost a smile. Okay. So this joke, it goes over with mixed, sometimes there's groaning, sometimes there's non-acknowledgement. It varies from class to class when I say this, but anyway. Can I erase? now finally, let's get back to the basics and do some more practice on our laws of exponents. So we're supposed to use rational exponents to simplify here. So this is from section 6.2. Numbers like 59 to 88. So I'll sample here. Number 60. We have the sixth root of t to the fourth. Number 66. We have the seventh root of cd to the 14th power. Number 71. We have the square root of x to the fourth y to the sixth. And number 72. We have the fourth root of 16 x to the fourth y squared. All right. Let's try to simplify these, yeah? Okay, so I will introduce the laws of exponents that we need as we go along, okay? So this we can look at as t to the fourth all to the 1/6 power. Okay? The law of exponents that I need to beg on to use here is if we have like a to the s to the t power, it's a to the s times t. So I can multiply the 4 times 1/6, and that gives me t to the 4/6, which is t to the 2/3, right? Which I think the game they want us to play here is to rewrite it using a radical at the end. So if I just said simplify and leave the answer in exponent notation, we'd be done. But they want us to leave the answer using radical notation. So using radical notation, this is the cube root of t squared. This one, I'm looking at cd to the 1/7 power raised to the 14th power, right? So again, using that law of exponents, this is cd to the what? 14 divided by 7, which is 2. Which, by the way, is c squared d squared. Now, there are other ways that you could have done that one, right? Another way you could have done this one would have been, like here's another way to go. Another way to go here would have been, this is the 7th root of cd to the 7th power squared. See, because 14 is 2 times 7. And the reason to do that would be, well, the 7th root to the 7th power is just whatever's inside the radicand again. So that's just straight up cd squared, which again is c squared d squared. You can have your truth, I'll have my truth, but we'll all have the same math. So math is funny that way. It's an enemy for people who want to have their own truth, I'm afraid. But math is kind of pesky that way. It's right or wrong. So this one, square root, remember, is the half power, right? So How would you, any ideas here? I think this one I'm going to use, this one what I'm going to do is I'm going to look at it, I'm going to use a property of square roots, which is that the square root of AB is square root of A, square root of B, yeah? So this is the square root of x to the 4th, square root of y to the 6th power, and then I'll fall back on that exponent notation, right? That's the half power. So I have x to the 4th to the half power and y to the 6th to the half power, right? Which is x to the 4 over 2, y to the 6 over 2, also known as x squared, y cubed. So that simplifies to x squared, y cubed. Last problem for today, over here. 4th root of 16. So here I'm going to use the property of the 4th root, which is the 4th root of a product is the product of the 4th roots. In particular, the 4th root, I got the 4th root of 16, the 4th root of x to the 4th, the 4th root of y squared, yeah? What is the 4th root of 16? Is blue chalk hard to see today?
Yes.
Sorry about that. Weirdly, it shows up better on the camera. Isn't that weird? Here, I'll rewrite it using...
I got it. Keep it
Oh, okay, so the 4th root of 16 is, well, 2 times 2 times 2 times 2. How many 2's did I get there? Anyway, 4 2's multiplied together gives you 16. So that's 2. The 4th root of x to the 4th, that's x. Ooh, but is it x? It's not x, is it? It's actually the absolute value of x. And the 4th root of y squared, that's y to the 2 over 4, which is, so you have 2 absolute value of x, y to the 1/2, or 2 absolute value of x, square root of y. Now I think that the book doesn't care about absolute value at this point, if I remember right. Number 72. Yeah, they just put 2x. So listen, the book has as its answer here 2x square root of y. So book assumes x and y are greater than 0 for the purpose of this example. It's just assuming that it's got positive variables, which is kind of obnoxious because it was just the last section they were making this big song and dance about the absolute value issue, and now they just don't care about it, which is, to use a word that my 5-year-old recently acquired, lame. But anyway, so anyway, if you write x instead of absolute value of x on this kind of problem, like on a test or something, it's not like, for most problems, it's not a big deal. There might be one problem in the test which is just about that, which would be a big deal, but for that problem. But generally speaking, if you put x instead of absolute value of x, I'm not going to think less of you or anything. I won't think less of you, whatever you do in math. I mean, this is just math. It's not, that important. Thanks, guys.